Hi, I'm Lucas Galindo, and I'm here to present performance benchmarking of local differential privacy for mobile devices. Privacy became a very popular field of study after the Sweeney analysis. Latonia Sweeney in 2015 analyzed counts of healthcare procedures done by public servants of the state of Massachusetts in the United States. And by combining two publicly available tables and some external data, she was able to identify which official had each procedure done, which was a major breach of privacy. After this work, uh, privacy became a major concern, and many ideas that were only theoretical until then were put forward and implemented by major companies. In fact, contemporary studies show that it's possible to reverse engineer uh, machine learning models that are available to queries to find out if a particular individual was present in the training data. This kind of attack is becoming more and more common, and the technology is making it easier. When combined with the needs to fulfill user data protection laws, this makes privacy a real concern in current times. Our focus is on differential privacy, which is not a algorithm or a technique. It's a requisite that algorithms and techniques must fulfill in order to be more resistant to this kind of attack. Uh, the goal of differential privacy is to make an attacker unsure if a given individual is present on a particular data set. If this requisite is fulfilled, most privacy concerns are mitigated. Machine learning algorithms and statistical procedures are subject to error, so the result of them is probabilistic. We want to manipulate this probability such that the odds of having a particular result are not really dependent on a single individual in the data set. Uh, the odds of the removal of a single individual from the data set to change the error in my algorithm is governed by a parameter called epsilon, or privacy budget. The mobile use case we want to analyze, we have a number of client devices sending reports through a communication network, which will probably be the internet. Uh, our server receives the reports, runs them through some stochastic algorithms, which just the name we're going to give to machine learning procedures, statistical analysis procedures, and producing an output O. Uh, Basically, to ensure differential privacy, we want to make sure that removing a single device from the network does not change significantly the output of the algorithms. The change is governed by the privacy budget epsilon. So an attacker can't really be sure of the change in the output was caused by the removal of single individual or by the natural error of statistical procedures. This model of differential privacy that focuses on the output O is very good against reverse engineering on the output O. but it leaves a lot of attack surface untouched. For an example, the communication networks, it does nothing to protect them. It does nothing to protect the data server where the reports received from the device are stored. It does not protect the against human error by the data analyst when publishing the output. These, i- these are all surface areas we want to cover. To cover all these threats, we go one step further and we apply the concept of local differential privacy. The privacy ensuring mechanisms are distributed through all the system, through client devices or servers that receive the reports. No data leaves the device to the server without being first encoded using a noisy encoding. So if one report is intercepted by an attacker, the data is too noisy for him to make sense of it. But the server, while aggregating a lot of reports over time, can use these noisy reports to do statistical analysis. On this paper, we're concerned with a single statistical analysis, heavy hitter identification. The devices have some variables, some string variables that we want to study. We want to identify uh, which values are most common on these variables. A value that appears on a lot of devices is a heavy hitter. We want to identify the heavy hitters with some certainty. Uh, Two scenarios are available. Well, let's think of, for example, model numbers. We have here on our backend a dictionary of model numbers. So we know that when a device reports a model number, it's a model number that is present in our data dictionary. This is not always true. Sometimes, like in a variable containing the most visited URL from a device, uh, the string can be anything. There's no data dictionary available to match the strings to. These are two very different scenarios from the point of view of differential privacy. Their algorithms need lots of adjustments to work in each scenario. Here we illustrate those scenarios. Under a non-dictionary scenario, all the devices select strings from a data dictionary containing a list of valid strings. This list is known to our server and used to our stochastic algorithms that will analyze the data. Under an unknown dictionary, each device generates its own string. Um, we Our stochastic algorithm must create a data dictionary from the received reports. Since the reports are noisy, the strings are somehow corrupted to avoid interception by an attacker. This data dictionary must be inferred using statistical analysis. It can't just be an accumulation of received reports. We want to evaluate two approaches. Google Rapport, which encodes data on the client device using Bloom filters. Those filters insert hash collisions on the data to make it noisy and prevent an attacker from parsing it. On the other end, the server uh, uses some heavy-handed statistical analysis to remove the noise and compute the heavy hitters. The other approach we want to evaluate is Apple's Hadamard encoding. This approach is much simpler. It is based on Fourier transforms. It's very lightweight on memory usage. Both approaches have known dictionary and unknown dictionary versions. Uh, Basically, expanding to an unknown dictionary version doubles the workload of the algorithms. Uh, Given these approaches, there are two metrics we want to evaluate. Accuracy in the statistical analysis. Since all the data is noisy, uh, the statistical analysis must do some noise removal to be accurate. We want to evaluate that accuracy. The second metric we want to evaluate is the time spent on computations. We have some time spent by the device to encode the data. We have some time spent by the server to receive, decode, and store the data. And we have some time spent by the server to parse the stored data and produce some statistical analysis. Here's our experimental setup. We have a client computer that emulates a Pixel 2 XL. The application on this emulated Pixel device reads some simulated data, encodes it, and reports it to the server. The report is sent via LAN to a server, uh, and then the operation becomes asynchronous. While the server is parsing the report to store it, the emulation receives ACK and terminates, and a new Pixel 2 emulation is started. This new Pixel 2 sends a new report, and so on. The process is repeated until we have sent all the reports we want to send. We are using a version of the algorithms with an extra step called circular chain encoding with fingerprint, developed by Samsung Research, to address the computational complexity of rapport and its need for large privacy budgets. Uh, Here we have the average processing time for each step we discussed before. Encoding a report on the client device, receiving this report on the server, decoding it and storing somewhere, and exporting statistics when a large number of reports has been stored on the server. The largest time required to encode a report on a device was on the unknown dictionary setting with rapport encoding. It was of the order, it was a bit below 1 microsecond. It was over 800 nanoseconds, 1000 nanoseconds. The largest time required to decode and store a report was also from the rapport on the unknown dictionary setting, which was of the order of 7,000 nanoseconds, 7 microseconds. Until then, all the numbers have no impact. We expect those numbers to be small enough to have no impact on the device operation or communication performance. The final step is the exportation of statistics by the server. This step can be seen as generating data visualization for a BI, so it doesn't need to happen in real time. The largest time required was of 2.5 minutes by the Hadamard encoding under an unknown dictionary setting. Now Now, to evaluate accuracy, we are going to use recall and specificity. Recall measures how many of the identified heavy hitters are actual heavy hitters on the data. In our case, the recall was almost perfect. Over 99% of the time, a string was pointed as a heavy hitter. It was an actual heavy hitter on the device population. Specificity measures the other way around. If a string was pointed as from the data, a string from the data dictionary was pointed as not being used by any device, how often is this correct? It varied a lot between 39% for rapport with a very tight privacy budget and small number of reports to over 66% with rapport and a privacy budget of 4 and 10 million reports. Now we see the results for unknown dictionary. We focus this analysis on the recall, the number of strings reported as heavy hitters that are actual heavy hitters on the device population. We see that the recall grows when the number of reports grows, and it also grows when the available privacy budget grows. But it grows very slowly. You need over 10 million reports and a privacy budget of 4 to have some good results. Final remarks. The unknown data dictionary setups are much harder to work with than known data dictionary setups. They have very reduced accuracy and take much longer to run. There's a trade-off between processing time and accuracy. Rapport encoding is much slower but has much better accuracy for datasets with over 10 million reports. Both algorithms are near perfect when you consider non-dictionary setups and the true positive rate. The true positive rate varied a lot between 3% and 100% in the unknown dictionary setups. Again, rapport with a large privacy budget and a large number of reports performs better but slower.